Chebyshevs theorem. This theorem is used to estimate the percent of data between a lower limit and an upper limit. We'll see an example here. I have a data set, and I've also entered this into my calculator into L1. And before we get too much farther, there are really two issues here. One is that this Chebyshevs theorem works for any, which is very important, distribution of data. We're going to be talking later in the course about distributions, in particular normal distributions, and we'll do a lot of work with that. This actually will work with any distribution, but there's a catch. We're going to be dealing with a variable k, and k must be greater than 1. If k is less than 1, it simply won't work. So the question is, what's k? If we look at our data, we can calculate our mean and our standard deviation. And we can do that using our calculator. We can just do our 1 var stats. And here's our mean of 34.33, standard deviation of 17.71. And we can indicate that in our data. I've already listed our data. So 34.3 would be somewhere in here. There's our 34.33, which is our mean. And we have standard deviation, which is 17.71. Now, upper and lower limits for Chebyshevs theorem, and this is actually going to be used quite a lot with other things, especially with normal distribution, is going to be increments of standard deviation. And what I mean is, what we can do is from the mean, we can move one standard deviation up and one standard deviation down. So if we did 34.33 plus 17.71, we would get our upper limit, which is 52.04. So this gets us here as our upper limit. And if we subtract this 17.71 from 34.33, we get our lower limit of 16.62. There's our lower limit. So we could go 2 standard deviations up. We could go half of a standard deviation up. We could go 3/4 of a standard deviation up and down. All right, this is always symmetric, both lower limit and upper limit. They're all increments of this standard deviation. So the question is, how much of the data is captured between this lower and upper limit? Well, we can count in terms of this. We start at 51, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14, 15, 16, 17, 18, 19. So we've captured 19 out of the 30 data points, which is approximately 67% between that lower and this upper limit. Now, if we wanted a particular percentage, or wanted a particular, or were given upper and lower limits and wanted to figure out what percentage that would be, that's what Chebyshevs theorem comes into play. To really get into Chebyshevs theorem, let's kind of start over a little bit. And let's formalize. We have, how do you actually calculate the lower limit? We take the mean. We can assume this is, I guess, a population mean. And what we're going to do is subtract a certain number of standard deviations. So we're going to represent that number as k. It could be 1 standard deviation, like the previous example. It could be 2. It could be 1.5, any fraction thereof. So it's k standard deviations. And, of course, the upper limit would be the mean plus k standard deviations away. So what Chebyshevs theorem states, it talks about this k value, right? Because depending on how many standard deviations you go from the mean, you'll capture more or less data. So percent captured equals, well, actually, I'm sorry, is greater than or equal to, that's very important actually, 1 minus 1 over k squared. You'll notice in the beginning I said that Chebyshevs theorem is used to estimate the percent of data captured. What this theorem tells you is that a number that is the minimum. It's at least this, but it could be greater. Right? Because it works for any distribution, it's conservative. Right? So you might actually have quite a bit more data captured than the Chebyshevs theorem predicts, but it won't be less. So that's how it's used. Let's look at a quick example so that you can see how it is used. Say we want to capture 58% of the data. The question is, what would the upper and the lower limit have to be to capture at least that percentage? Well, this 58% goes into this part of the inequality, and you would want to use the relative frequency form, so 0.58. 1 minus 1 over k squared. Now it's a matter of solving for k. I'm going to rearrange a little bit. Move 1 over k squared over here. Move the 0.58 onto the other side. All right, that turns out, of course, to be 0.42. Going to invert both sides, and that becomes 2.38. And then, of course, square root both sides, and this becomes 1.54. So if we want to capture 58% of the data, we now can calculate what the lower limit would have to be. We take our mean of 34.33 and we're going to subtract 1.54 standard deviations. And we end up with this lower limit of being 7.06. And then, of course, we do the same thing with the upper limit, only instead of subtracting, we're going to add the same number of standard deviations away. And our lower limit will be 60, or upper limit, sorry, will be 61.60. I moved the calculations just so I can show where the upper and the lower limits are. So 61.6 means here's my upper limit, and 7.06 means there's my lower limit. So all this data between is the data that's been captured between those lower and upper limits. And if we look at it, we can actually count 2, 4, 6, 8, 10, 12, 14, 16, 18, 23. So we have 23 out of 30, and that approximately equals, what do I have? 0.767. So that's going to be about 77% of the data. Put that up here, 77%, has been captured. All right, notice we wanted to capture 58%. And that's where this inequality really comes in. Remember that Chebyshevs theorem produces the minimum. Right? So is it at least 58%? Yes. It could be bigger, like 77%. But what we calculated is the upper and lower limit that it would not be lower than 58%, depending on, again, how the distributions really are. Now let's do another example. And for this next example, let's start with our data again. And instead of looking for the upper and lower limits for a certain percentage, let's start with the lower limit. So given that the lower limit is, for example, 10, and the upper limit is symmetric with the lower limit, we could figure out, well, what percentage of the data could that be? So what we need to do is, again, that we're working a little bit backwards. Here is 10. We have to figure out, this is k number of standard deviations, and we have to figure out what that distance is. So we can pretty easily go 34.33 minus 10. That, of course, is 24.33. So we know that that's 24.33. Well, we know that standard deviation is 17.71 in this case. 24.33 is a distance. We can solve for k pretty easily. We divide by 17.71. And we end up with a k value equaling 1.37. Now at this point in time, I want to emphasize we need to pause and say, well, remember, Chebyshevs theorem only works for k values bigger than 1. We have to check, is this bigger than 1? Yes. If at this stage we get a value that's less than 1, then we can't use Chebyshevs theorem. It won't work out. So as long as k is bigger than 1, we can continue. Well, now we can simply do percent captured. We know our Chebyshevs theorem. All we have to do is plug in the number and then crank it through our calculator. That's going to turn out to be, I'll give you some intermediate steps, and then this is, of course, 0.47. So that would be 47% of the data would be captured between 10 and its symmetric lower level, which we didn't even find. It would be easy enough to find. This would be 34.33 plus, now that we know what k is, we could now calculate what that is pretty quickly, which turns out to be 53.6. And in fact, we can now calculate the actual percentage. Now, is the actual percentage going to be the same as 47? No. Again, it could be bigger. It's actually likely bigger, but it wouldn't be less than 47. Counting these up, turns out there are actually 20 data points between the lower and the upper limits. That'd be 20 out of 30, which is, of course, 67%. which is bigger than 47, but is not less. And that's really all that Chebyshevs' theorem states.